let's start. uh, Today, I'm going to talk to you about human hearing system or human auditory system. Well, of course, on the base of latest, you can see, okay, but the same problem. I don't know what's going on. How about this one? It works, yes. And how about the changes? Okay. So today we are going to talk about human auditory system. So one of your colleague from higher year, I think the last year, yes, taught as an anatomy lesson. So I tried to make some this presentation as useful as possible from the transmission point of view. Not so. It's not to be some kind of anatomy lesson, but some medical things must appear in my presentation. Okay, so the human auditory system contains two main parts. The first is peripheries. So I mean the ear, left and right ear, and the second one is a central auditory system. And this central auditory system is simply the brain. So it's some sensory and some neural stage of analyzing of every signals perceived by human sensors, not only in the hearing domain, but also as a temperature and light and for example you taste, etc. So the ear contains of three main parts. First of all, this is the outer ear, presented here in this pink color. The middle ear, here in this area, and cochlea, this a kind of snail in orange. And the outer ear consists of three basic elements. The first of all is a pinna. A pinna means this this part of the outer ear, which everybody can see. And after this, the sound wave goes through the ear canal, and the last element of the outer ear is a eardrum, and we can call this as a tympani membrane. And as every organ in a human being, the outer ear has some functions. First of all is localization of the sound source, and this localization is possible mainly by the shape of pinna and on the base of the differences between signals, acoustical signals, going to the right and left ears. And another function of the outer ear is a protection of eardrum, because the eardrum is at the end of this outer ear, and this eardrum is placed in the middle of the head, and it vibrates. Mainly, it vibrates some special conditions related to humidity and to the temperature. So it is also protected by displacement from the some mechanical shocks, etc. And the last main function of this part of the ear is amplification of the sound. And this amplification occurs in the range of 1 to 3.4 or 3.7. The last value differs in the biography, but we can simply say that it is a limiting frequency of 3.4 kilohertz, and this amplification occurs due to dimensions of ear canal. So the ear canal looks like some kind of organ pipe, or a very little organ pipe. So it has some resonance, and this resonance occurs in this range of frequency. I mean, from approximately from 1 kilohertz to 3.5 or 4 kilohertz. And the frequency of this region are slightly amplified by about 2 or 3 or 6 decibels. And of course, this dimension was created by the evolution of the human. For example, in the elephant, the resonance of outer ear external canal is about 100 hertz, and because in elephant, in the case of elephant, this ear canal is bigger in comparison to the human. And of course, it's necessary for the existence of the elephant, as well as for the communication of the humans, simply. So this range of frequency boosts and improves some kind of pronunciation and some kind of formats responsible for a good understanding, mainly of the speech. So the next week we'll be talking about the speech and speech signals. So more details about speech signal will be presented in the next week. Well, after this, the sound waves goes through the ear canal. At the end of ear canal, we can find the eardrum, and eardrum starts to vibrate, and vibration is transferred from the air to the middle ear. And middle ear consists of middle ear cavity, ossicular chain, which consists of malleus, incus, stapes, and this osticular chain and these little bones are mounted to the middle ear cavity by the muscles, and the most important are the stapedius muscle and tensor tympani muscle, and of course the middle ear contains also a Eustachian tube. Let me tell you something about uh, these these elements. In this picture, you can see the cross section of or some schematic view of the middle ear. So, as I said, the sound waves uh, causes some vibration of the tympanic membrane or eardrum, and malleus, the base of malleus is connected to the eardrum, and it together with this tympanic membrane starts to vibrate, and this vibration is transmitted to the incus here, and from the incus to the stapes, and the base of the stapes is laying on the oval window, which is the entrance of the inner ear, and it is the entrance uh, uh, into the sensory part of the human organ of hearing. And so these three ossicles, malleus, incus, and stapes, are uh, connected to the rest of the bone with some ligaments, as well as a stapedius muscle and the tensor tympani muscle. And of course, the middle ear cavity is connected to the throat via Eustachian tube. And the general function of middle ear is a feeding of acoustical impedance. The second one is a protection against high sound level. And the third one is equalization of static pressures between outer and middle ear, particularly the changes of static pressure from both sides of a tympanic membrane. And the fitting of acoustical impedance is based mostly on two effects. Effects of lever and effect of piston. The effect of piston is connected to the difference uh, in areas from the tympanic membrane and the base of stape. I mean, it is the area of the base of stape is equal to oval window, and so it works in this manner, and this acting is explained in this picture. And protection against high levels of the sound is mainly based on stapedial effect. So the eardrum or tympanic membrane becomes more rigid because of action of tensor tympani muscles and stapedius muscles, and this fact results that uh, the efficiency of vibration transmission from the air to the inner ear is lower, particularly for higher sound, and it prevents to to higher level of vibration going to the going going to the inner ear, which may cause permanently damage of some hair cells in this part of the hearing organ. And so the feature of stapedial effect um, are time of response, it is 150 milliseconds, time of relaxation 1.5 seconds, as well as a level of reaction. So this effect starts to be active at 85 decibels. And of course, when the level of the sound gets lower, so stapedial effect disappears, and the relaxation time is, as I said, 1.5 seconds. And the equalization of static pressures from both sides of the tympanic membrane is provided by Eustachian tube. Uh, of course, it has the time constant, and when the static pressure changes rapidly, for example, during taking off or landing of the plane, or going with some fast elevator, the equalization cannot appear immediately, and so you can know that you can feel some unpleasant pressure inside the ear, and the sound perception becomes worse for a moment. And of course, this when this equalization starts to work, so this unpleasant effect disappears. And with some vibration of the base of stapes, uh, we go into the inner ear, which consists of which are constructed of two main parts. The first is semicircular canals with some equilibrium sensor, and the second one, the most interesting for us, is a cochlea and auditory nerve. So that is a center of sound perception sensors. And this cochlea can be presented as some kind of rolling off this shape, and we can see the oval window, and on this oval window there is the base of the stape, and the round window, which vibrates in antiphase in reference to the oval window, because we have here some gap in the top of the cochlea, and from scala vestibuli, some vibration goes through this gap, which is called helicotrema, and we have also scala tympani, and in the middle of this cochlea we can find the scala media. And in real view, schematic view, we can see as in this picture. We have scala vestibuli, scala tympani, scala media, and there is a basilar membrane here. And of course, some kind of nerves which are formed into some nervous channel, and this nervous channel goes directly to the to the brain. And the cochlea, some facts. The space between oval and round window is filled by perilympha, and perilympha is rigid fluid. So it is necessary to fit the impedance between the air and rigid fluid, because when this impedance fitting doesn't exist, uh, the great part of the acoustic energy should be reflected by the by this fluid, because of the great differences in acoustical impedance. So it's necessary to fit impedances, and this fitting is provided by mainly by middle ear. And scala media are filled as you remember, the scala media is in the middle of the cochlea, and these scala media are filled by endolympha, and the concentration of ion of sodium and potassium is different than in perilympha. So we have some kind of a contact potential between two liquids, and this potential is circa plus 90 millivolts. And the basilar membrane lies on the bone shelf. You can see on this picture some schematic cross-section of the cochlear canal. And once again, we can distinguish here scala vestibuli with perilymph, scala tympani also with perilymph, and please remember that the scala vestibuli and scala tympani are connected at the top of the cochlea, and this is a helicotrema. It is a little gap which connects the scala vestibuli with scala tympani. And in the middle of the cochlear canal, we can find the scala media with endolymph. And Reisner's membrane is some barrier, some border which divides these two kind of fluid, perilymph and endolymph. And we can find also tectorial membrane and basilar membrane, and between those two membranes we can find the outer hair cells as well as inner hair cells. And these two kinds of hair cells are very important from the sound transmission, very important for sensation of the sound. In this picture, you can imagine how it works. We have here a basilar membrane, and outer hair cells as well as the inner hair cells, one side of each kind of hair cells is connected to the basal membrane, and the other end is connected to the hair density membranes. So we can name it as a textural membrane because there is some kind of cover net. And when sound goes to the outer ear, goes through the middle ear, and it's transformed from the sound wave into the mechanical vibration. So this vibration is transmitted via basilar membrane in the form of a running wave, and this running wave causes the movement of one kind of inner hair cells as well as the outer hair cells. So when this cover net is relatively constant, in this position. So these hair cells are going to move from the one side, and so this movement causes that some canals should be opened, and the polarization causing some neural impulses, electric neural impulse can be active. So when basilar membrane moves, the impulses are created mainly by inner hair cells and by the outer hair cells due to the polarization made by difference in potentials between endolympha, because endolympha is in this on the cover net, and perilympha, which is in the area of basilar membrane. And how about these hair cells? We can divide it, these cells into two groups. The first is inner hair cell, and it's placed in one line. The total number of inner hair cell is 3,500, and which of them has from 30 to 60 hairs, and this kind of hair cells convert mechanical vibrations on electrical impulses. And another kind of hair cells, it is outer hair cells, and we can say that outer hair cells are situated in 3 or 5 lines. It depends on particular person, but the total number of outer hair cells is 30,000, and every cell has 100 to 140 hairs, and it kind of this kind of hair cell provides feedback between the central auditory system and the ear. So inner hair cells transmits. We can say that due to conversion from the mechanical vibration into some electrical impulses. So we can say also that inner hair cells transmits signals from the from the outside of the head into the brain, and outer hair cells works as a feedback, and outer hair cells transmit signals from the brain to the periphery parts of the human hearing system, and this periphery, I mean that it is a middle as well as the outer ear, particularly the tympanic membrane as well as a stape. So the stapedial effect is possible to work due to outer hair cells activities. Well, this cross section of the organ of Corti, because this element of inner ear is often called as a organ of Corti. You can see that one more time that we have some basilar membrane and one row of inner hair cell and 3 rows of outer hair cells here, and textural membrane. And one more time, I can remind you that here we have perilympha, and in this part, when the textural membrane ends, we have endolympha. So two ends of outer or inner hair cells are connected to both kinds of this liquid. So endolympha or perilympha here. Well, how the basilar membrane moves. So the movement of basilar membrane is exactly connected to the frequency. You can see that the shape of displacement of basilar membrane is a result of frequency values. So for the lower frequencies, we can observe the maximum of displacement occurring at the top of the cochlea. So at the end of this basilar membrane, while when the frequency value increases, there is the shortening of the of the distance between the active or maximum displacement observed and the beginning of the basilar membrane is also observed here. So for lower frequency, the maximum of displacement is observed in the top of the cochlea, while for the higher frequencies, the maximum displacement is observed near oval window or near the base of stape. And so you can see in these pictures, on these two pictures, uh, some kind of hearing cells, of course, in a great zoom. On the left, three rows of outer hair cells, and on the right, one row of inner hair cells, as well as three incomplete, or I mean damaged outer hair cells here. So in a good condition of the hearing organ, we can find the hearing outer hearing cells in this as a V shape, and when they are damaged, we can we can find some gaps between the row of inner hair cell as well as uh, other parts of basilar membrane. So, as I said, the ascending auditory pathway from outer ear into the brain, it goes mainly by the inner hair cells, and descending auditory pathway works mainly due to outer hair cells. So you can find that from the brain is going down by the cochlea. And so what the feedback means and what it can cause. First of all, the selectivity of hearing depends on the condition of outer hair cells, and the results are presented here in this picture. You can observe that in vivo organism we have a great selectivity in comparison to the dead organ. So post-mortem, we can find that selectivity of the hearing and sound pressure, which is necessary to make some acts of hearing, is um, is worth about 40 decibels. So the energy of the sound uh, should be uh, 100 times higher for the dead organism in comparison to the alive, as is presented here. And of course, you can see that in this case, I mean in vivo, we have some very steep activities, and it means that accuracy of frequency discrimination or some sound object discrimination is more accurate in comparison to the post-mortem receiver. I mean, this kind of curve. Uh, this curve is not so steep, so it is the quality factor. We can say that the quality factor of the dead organism is lower than in the case of alive mechanism here. So it's this difference is caused mainly by the activity of outer hair cells. So it means that this feedback is very effective. And uh, the auditory area, which can perceive the sound, lies between 20 hertz and approximately at the 16 kilohertz or 20 kilohertz, and ranges from the sound pressure levels about 0 decibels, and the maximum values of sound pressure levels can be about 100 decibels. And this auditory area is limited by so-called the threshold of hearing here, and the uncomfortable hearing, or the threshold of pain for the higher SPL values. Of course, uncomfortable listening, as well as the threshold of pain, are very difficult to measure, because some sensation of the people could be different, and we can be very careful to to measure this kind of threshold, because of risk of damage of hearing organ. And so for our considerations, very important is threshold of hearing. I mean, this border of the auditory area. So the threshold of hearing means that there is the smallest sound pressure which is necessary to make some auditory sensation for particular frequency. You can notice that for different frequencies we have this threshold of hearing of different values of sound pressure levels. And between the threshold of hearing and the threshold of pain, we can find about 100 so-called equal loudness curve. So there are some lines which connect the points in the frequency domain that for particular sound pressure level, the sensation of the loudness is equal to the same measured for 1 kilohertz. So, for example, when we are talking about equal loudness curve number 50, means isophone 50 phones. So we can compare the loudnesses caused by, it is the same loudness, but with different intensity or sound pressure levels necessary to make the same sensation for different frequencies. As you can see, that from lower frequencies up to towards the higher frequencies, we have very different values of sound pressure, which causes the same sensation of the loudness in comparison to 1 kilohertz. And so this kind of equal loudness curve is called isophone and means and the unit is a phone. Okay, but as I know, you cannot meet the isophones during your laboratory exercises. So it's only fact for you to know that the range of total hearing area contains a little more than 100 phones as isophones as a equal loudness curve. And more important things is a threshold of hearing. Presented here in dashed lines. And so you can find here two kinds of curves. It depends on the measurement scenery made by, for example, in this case, Robinson. That's on the names of two researchers, and this is a recommendation by the International Standards Organization, and this is a red line. And so our interest right now will be this kind of this curve and presented in this dashed line. And this is a minimum level which causes some auditory sensation. And as you might have guessed, this minimum level is different for each frequencies. And of course, talking about the threshold of hearing, we can also talk about some masking phenomenon. The masking phenomenon, with this phenomenon, we can meet when we have two signals. One of them is our useful signal, and the second one is a masker or masking signal. For example, this situation occurs for example, on the traffic, when you talk to each other and some very loud cars or trams are going, and so the noise made by these cars don't allow us to communicate. So this situation causes that the threshold of hearing goes up when the masking signal is presented here. In the schematic view is presented in this picture, but this plot is more precise. You know, if we don't have the masking signal here, this signal, this black signal, as for example sinusoid, is simply presented because its pressure, its sound pressure level is higher than the threshold of hearing. And when masking signal starts to work, the threshold of hearing near the masking frequency, the threshold of hearing for this frequency goes up, and you can find that original signal, firstly audible, uh, becomes inaudible because its sound pressure level is lower than the hearing threshold in the case of the masker. So the masking is such kind of acoustic phenomenon that that increase the threshold of hearing for some specific condition. So in a frequency domain as well as in domain of intensity also. Well, this signal can be audible again if sound pressure level for this signal will be higher or will be greater than this threshold. In this case, it's called masking threshold. So more precise, it should be masking hearing threshold. Because the hearing threshold normally without masking is presented here in the dashed line, and masking hearing threshold it's a new hearing threshold in the case of presence of the masker. So this signal will be audible again when its sound pressure level will be greater than this masking threshold. In this case, I think it's about 15 or 20 decibels. So this signal will be audible again, but without increase of sound pressure level, this signal remains inaudible in the presence of the masker, of course. And we can talk about two masking conditions. First is tone-to-tone masking, and this is a specific kind of masking which exists only in a laboratory, or it's very hard to find this situation in real life. But it features in the character for the masking curve for lower frequency than the masking frequency or the higher frequencies. So from the lower frequencies, loud sound will mask sounds of higher frequency only, and for the lower frequencies, the influence of the masking tone is lower than for the higher range of this frequency. And so softer sounds will not mask or will mask some useful signals in a less effective way than the louder signals. And another kind of masking is noise tone masking. When we have detect some tones or some useful signals on the base of the noises. I mean that the noise is most often kind of the sound we can meet in real life. For example, as I said, traffic or in some loud crowd, etc., etc. So when we have noise as a masker, we can find that masking curve is more symmetrical in comparison to tone masking. We have here a very steep and a rather flat for higher frequency masking efficiency. And in this case, we have almost the same, but a slight difference. Let's assume that these curves are mostly symmetrical, and so you can see that for frequencies lower than the masking frequency, we have a similar situation than for tone-to-tone masking. And for higher frequencies, we also have the same situation, but let's take a look for this curve, for example. When we have a masker of 410 hertz, and there is no masking effect, and the level of the masker noise is 70 decibels. So the efficiency of the masked signal of the frequency of 1.5 kilohertz is equal to 0. And so it means that the masking occurs only in a narrow band of the noise. And so at the portal, you can find some demonstrations. And so I recommended you to listen to these demonstrations because in normal lecture I used to play this demonstration for the listeners, and it simply explains what's going on during the masking phenomenon. And so, if you listen to this demonstration, I think that everything will be clear. And it's the fact that only the narrow band of noise has the influence of the threshold increasing of the tested tone, or as I said at the beginning, of the useful tones. The shape or the range of the masking signals, or the bands which are effective in the masking process can be found in many experiments. So you can see in these pictures that the bandwidth of the masking signals, masking noise, made different independent on the authors which made some experiments, but the character is almost the same. The bandwidth of the masking signals, masking noise, increases when the central frequency increases too. So when the central frequency increases, increases, so the bandwidth of the masking noise increases too. And so this bandwidth reaches from uh, 50 hertz up to several kilohertz for higher frequency central frequency values. And the concept of critical bands, because someone had an idea that critical bands should be considered as auditory filters. So as filters of frequency analyzers, so similar to some analog filters, you know, you know what I mean. So the concept of critical bands described the frequency bandwidth of the auditory filter created by the cochlea, especially basilar membrane. And this is, of course, the organ placed within the inner ear. And so the critical band is the band of audio frequencies within which a second tone will interfere with the perception of the first tone by auditory masking. So when masking occurs, so this interference will be effective, and the results will be audible of this interference. And this interference may occur only within one critical band as a filter. And there are two main facts for critical bands as auditory filters. First of all, it's that the efficiency of masking is stronger within critical band in comparison to the area outside the critical band. So, of course, it's connected to the bandwidth of noise masking the signal, and you can find it listening to the experiment I recommended you, and this experiment is in ePortal, is posted in ePortal. And the second important fact is that the particular critical band is created by the acting frequency of the audible tone. So, the central frequencies of particular critical bands are not constant. And when we have some stimuli with some specific frequency, so our hearing system can create the critical band around this acting frequency. And due to basilar membrane, we can find that the number of critical bands for human is 24. And one critical band refers to 1 millimeters of the basilar membrane length. So we can simply say we can say that basilar membrane has 24 millimeters length. And another kind of auditory filter is introduced at the end of previous century. I mean, in the 90s. And it is a equivalent rectangular bandwidth. And the scientist which introduced these ERB filters, assumed that the bandwidth of single equivalent rectangular bandwidth refers to 0.8 millimeters of the basilar membrane. So the total number of ERB is 32. So the difference between ERB and critical bands is that there is more filters due to ERB analyzers and in comparison to classical critical band theory introduced by Zwicker in the 40s in the previous century. So let's talk a few words about pitch perception. You know, our previous consideration on the masking referred to the loudness perception and the threshold of hearing. But another recent attribute is a pitch sensation. For example, if you play some instruments or when you sing some melody, you can use the frequency for determination of the pitch produced by instrument or by your voice, and and somebody can listen to your performance and on which base he or she can perceive the pitches you produce. So there are two theories of pitch perception, two important. First is the place theory, and the second one is so-called temporal theory. So the place theory is connected to the basilar membrane displacement for a particular frequency and is based on the fact that different frequency components of the sound stimulate different places along the basilar membrane, and in turn auditory nerve fibers with different characteristic frequencies. And so once again the picture which can explain the displacement of particular places, particular places in the basilar membrane, independence of the frequency. And the temporal theory of pitch perception is based on the phase locking mechanism and perception of time intervals between successive firings which are produced by the stimuli, and the successive firings occur at approximately integer multiplies of the periods of the waveform. So in this way, the waveform periodicity that occurs at each place of the basilar membrane is coded. It's coded as a number of neural impulses, and at some point in the auditory system, these time intervals have to be measured, and on the base of these results of the measurement, some pitch impression is created. So, to be frank, none of this theory completely explains how in which way we produce or we perceive the pitch of the sound. The mm, when we use two theory, two theories mentioned earlier, we can explain many things, but not, but it's not some universal, some universal explanation. You know, so. Uh, One of my friends, who works in the psychoacoustics, mm, said that it's only our hypothesis to describe some mechanism of perception, and we we can be sure how we can perceive a lot of sound uh, with uh, um, with the electrodes connected directly to the brain, and so we can expose the subject for the sound, and we can record all the impulses, and so we can be more sure than now on the act of the process of sensation of sound perception. So you know, it's only some kind of theories, but none of them are uh, mm, can be true in a real life. Yeah. Unfortunately, of course. So it's only the result of some kind of experiments and some kind of assumptions, etc. So another example of some attribute which is not clear in the perception is a type of the sound or sound color, and this is a multidimensional feature of sound and depends on spectrum, envelope, direct, and the balance between direct or indirect sound, and the type of the sound allows the listeners to distinguish particular sound sources in a whole soundscape. And of course, I also recommend you to listen to some presentations from ePortal, and there are two presentations of connected to the timbre. First of all, it's a synthesis of the sound of two instruments. And the second one is more interesting, and it contains the piano sound played backward and forward, and the impression of the sound color is completely different when the sound is played forward or backward, except for the same melody, which is played by this instrument. So I recommend you to listen to this presentation, to this demonstration from ePortal, because this demonstration confirmed that sound color is a multi-dimensional feature of the sound, and everything influence this feature as a product of impression. And so let's go back for the moment to our auditory area. So as I told you earlier, we can talk about auditory area when we have the sound of frequencies from ranging from 20 hertz to almost 20 kilohertz, and from the intensity or some pressure levels range from 0 to 110 decibels. And within it, with area, we can talk that we are in auditory area. So every sound which has frequency from this from this range, as well as a sound pressure level from this range could be perceived. And how about the people with some hearing loss? Well, they don't perceive the whole auditory area in comparison to the healthy man, and they perceive the area of sound which are limited from the upper of by the pressure of the pain, and from the bottom on the hearing threshold. Because in normal hearing we can talk about hearing threshold from 0 decibels to 70 decibels for the lower for the lowest frequencies. And when we compare for some disabled people, we can find that the minimum sound pressure level causing the auditory sensation is about, in this case, some sample view, it is about 25 decibels. So the hearing threshold is higher comparing to normal hearing. And how about this examination of the hearing condition is possible? Well, you can find it by yourself during your laboratory. You have some exercises of audiometric measurement, and let me tell you a few words about some audiometry measurements. So we have many kinds of audiometric measurements, and you can work on pure tone audiometry. Pure means sinusoidal, so we can use some sinusoidal tones of 8 frequencies from 250, 500, 1 kilohertz, 2 kilohertz, 3, 4, 6, and 8 kilohertz at the end. And the test of pure tone audiometry is conducted in a sound with the use of a pair of foam inserts or supraoral headphones connected to the external audiometer, and this audiometer is usually operated by independent people, not for the person who is under measurement. And for the test, pure tones, I mean sinusoidal tones of specific frequencies and volume are delivered to one ear, mostly to the one ear at a time, and you are asked to signal to answer when you hear a sound. So when the auditory sensation is in your mind, you can signal, or you can say that you perceive the signal and your response is noted. Of course, such conditions as a frequency or sound level at which you can perceive this sound is noted, and we can make some pure tone audiometry with the use of air conduction as well as bone conduction. And so, bone conduction comes from that our head could vibrate when exposed to the sound wave, and this vibration of the bone is transmitted directly via asticles to the malleus, incus, and stapes to the inner ear, and so we can imagine that we can hear the sound, but we uh, rather feel this sound, you know. Uh, and so this is bone conduction, and we use the bone, artificial mastoid, instead of the earphones for this kind of examination. And this mastoid transducer is placed usually behind the ear. And for examination, we need some diagram to plot your real responses in a frequency domain. And this chart shows also 125 hertz, but it's for special purposes. And as I know that our audiometric device used in the laboratory doesn't allow to measure with this frequency, and your experiments will start from 250 hertz. And so the results of the test is called an audiogram, and this is a diagram which plots a person's hearing sensitivity at the tested frequency. And when you have a normal hearing, it means that your hearing threshold ranges from minus 10 decibels, so you can hear better than a standard threshold of hearing, and you can hear the stimuli of the level of 20 decibels, and so it's still called that you have a normal hearing. And some details. The y-axis represents intensity measured in decibels, and the x-axis represents frequency measured in hertz. Threshold of hearing is plotted relative to a standard curve that represents normal hearing in decibels, HL. And in the next slide, I can explain you in details what this unit means. So dB HL are not the same as dB SPL and resulting equal loudness curve, which are a set of curves representing equal loudness at different levels and expressed in sound pressure levels, decibels. For humans, normal hearing is between minus 10 decibels HL and 15 decibels HL, or some uh, some sources assume that 20 decibels is also a normal good hearing, and the range of frequency is from 250 hertz to 8 kilohertz. And let me explain you what these kind of decibels mean. So dB SPL, so decibels of sound pressure level, means, according to this formula, when PO is a reference and it is 20 micropascals. So when we have this dashed curved dashed line, when we make this line flat, we can have some standardized by international standard organization, so-called the normal hearing threshold, and this is the reference for audiometric measurements. And dBHL here in this audiogram, this flat line refers to the threshold for special frequencies here, without some differences in SPL values. And the last used in psychoacoustic unit is decibels SL as a sensation level. So the reference is the hearing threshold for particular subject. You know, the difference between dBHL and dBSL is that dBHL is for normal hearing threshold obtained for a large group of subject, and there are in good hearing, and so normal hearing is defined for people of about 20 years old, but sensation level could be measured for everybody. And so when we have somebody with some hearing loss, sometimes easier for us is express that and use the unit as a dBSL, as when where the reference is the actual hearing threshold for this particular measured person. I mean that when we have 5 subjects and everyone has different hearing loss, hearing losses, so dBSL could be also different for the same stimuli condition. But in your laboratory, you will use dBHL, and it means hearing level with the reference of normal hearing threshold, and which is a subject of the standard by international standard organization. And when we have some Puritan audiometry results as plotted in this audiogram, it means that you feature normal, good good hearing. We can use other kinds of ear examination. For example, speech audiometry, which is based on the ability to detect and to repetition of the spoken words at different volumes, and normally the audiologist will ask you to repeat a list of words to define your speech reception threshold or the lowest volume at which you can hear and recognize the speech. And the audiologist will measure speech discrimination, also called word recognition ability, and he or she will either say words to you or you will listen to a recording and then you'll be asked to repeat the words. And the results is very often as a speech discrimination ability and is expressed as a percentage score of correct answers. And tonal, pure tone audiometry, as well as speech audiometry, are called the subjective audiometry measurements. And the example of objective audiometry measurement is so-called immitance audiometry. And the test measures the function of the eardrum and the flow of sound through the middle ear. And it's based on this technique that a probe is inserted into the ear canal and air is pumped through this canal to change the pressure within the ear as tones are produced. And so, have you met some phenomena that you can, from time to time, you can listen to some tone coming, or you can listen to some tone without any stimuli, and it's some impression similar to immitance audiometry that you especially in a range of frequency about 1 kilohertz, you can imagine that you listen to the tone, but there is no source of this signal, and so the reaction of this signal is objective, and it's controlled by the outer hair cells activity. And so this kind of objective measurements without the mind of the subject, as it is as this mind is involved in pure tone audiometry as well as a speech audiometry. Well, so that's the end. And most important things to remember from this anatomy lesson. So the construction of the ear, it is the first thing. The functions of outer, middle, and inner ear, the inner and outer hair cells and their role in hearing process. And in the test I like to ask about the total number of particular kind of cells. So, what's the base of masking phenomena, and what's the phenomena and connected to the critical bands, and what's the assumption of the critical bands also? Equal loudness curves and audiometric test will be for you, especially for laboratory exercises, in particular pure tone audiometry. And for those of you who want to have some more details on the hearing process, I recommend you two books: Brian C.J. Moore, An Introduction to Psychology of Hearing, and the second one is Henry Dillon, Hearing Aids. So that's all for today. I think that everything is clear, and if you have some question, please give me this. Well, if everything is clear, so have a good afternoon, and so see you next week. I'll be talking to you about speech and speech signals.
Thank you. Goodbye.
Goodbye.
Thank you. Goodbye.